안녕하세요 여러분, 해리입니다. Today we're going to learn calculus, which is one of the most important topics in IB mathematics. So calculus is mainly divided into two different parts. First, differentiation, and second, integration. We use calculus to find some of the geometrical aspects of a curve. So for example, local maximum, local minimum, tangent with a certain gradient, or area under the curve. We start with differentiation first. So differentiation is basically looking for the gradient of a curve. So mainly we're going to look for the gradient. So let's recall how we could calculate the gradient. So in linear functions, computing gradient is very simple. We just need 2 points. And the gradient will equal to the change of y over change of x, rise over 1. But now, not all functions are in linear, which means that if we have a curve like this, and let's call it as fx, and what can we do if we want to find the gradient of this certain curve? So like what we have done for linear, let's try to find some points. So since this is fx, this y value will equal to fx1, and this will be fx2. So like what we did, the gradient will be approximately this. Note that this is just an approximation, it's not an exact value of the gradient. So by finding these 2 points and doing what we did for linear, we could possibly get a similar gradient, but not exact. Then what if we want an exact value of a gradient? Then let's recall how we could find the area of a circle. So area is always defined as the base times the height, which means base times the length. So we always needed a perpendicular line and a straight lines. But a circle, as you can see there, it's all entirely curved. So how we could find the area of a circle? We divide this circle into infinitely many sectors. And then make them into a parallelogram, like that. And note that if we divide this circle in infinitely many sectors, and if we add up like that, then in fact it looks like a rectangle. So this must be the radius, and the entire circumference of a circle is 2 pi r, but note that half of the circumference goes to the top and the other half goes to the bottom, so the width will be pi r. That's why area of a circle is pi r squared. And let's use this idea to this. So again, we have a curve, and this time we are not going to use 2 different variables, but instead let's say we have x here, and let's call the change of x as delta x. Then this will be x plus delta x. So we put this x into this function, then the output will be fx, and So this y value will be fx plus delta x because the input is this and it's the function. So let's use the approximated gradient again. So the gradient will approximately this. And if we clear this a bit, we have this. Now, how we can apply this to here. Okay, so this is a curve and we want to find the gradient using these 2 points. Then why don't we make this delta x very, very small so that this curve will look like a linear part. And how do we express that mathematically? We write it as limit delta x tends to 0 fx plus delta x minus fx over delta x. And this will equal to the gradient. So that means by using this, we can find the exact value of the gradient. So we don't need any approximation anymore because we can find the exact value. Oh, and note that this limit is not really the same with sigma or all the other notations. So what this means is that for every delta x you see on the right of this, then delta x tends to 0. So all these 2 delta x tends to 0. That's it. So for example, if you have later, if you have something like let's say delta x, just an example, something like this, and multiple things, then for all delta x this holds. So it's just saying that delta x, it's just telling you what delta x is. Alright, so that is called the first principle of differentiation. And in some of the textbooks, so some of the IB textbooks like Cambridge, they use h instead of delta x. So just replace all delta x by h. And this will equal to differentiated version of fx. And in fact, there are some more notations to indicate differentiation. So this f prime x or dy over dx if y equals to fx, and we can also make it as y prime. Personally, I recommend you to use this notation because it has more information. So it has more information. So what this means is that dy over dx is basically saying the instantaneous change in y in respect to the instantaneous change of x. So we can also see what y is differentiated with. So change in y. And note that it's not just this delta. So delta x doesn't necessarily, it doesn't have to be instantaneous. So we can see that the change could be very large. But for this dx, this change has to be very, very small. very small. So dx and delta x are different thing, and they're equal when if and only if this delta x tends to 0. So if it's almost the same as 0, then this holds. So that's the definition of differentiation. And now let's move on to see some examples. So let's start with a very simple curve like y equals x squared. So I'm pretty sure everyone can sketch it. So it looks like this. And before we directly compute the gradient, let's try to see what it will look like. So when x is negative, the gradient is clearly negative because it's decreasing, right? And then when x equals to 0, the gradient becomes 0 because it's a flat horizontal line. There's no change in y, so the gradient must be 0. And on the positive side of x, the gradient increases back. So we can kind of estimate that the gradient will start with negative values, and then it will become 0, and then it will go positive. Now let's see whether it really works. So recall the first principle of differentiation, where, okay, so we have y here, so let's use dy over dx. It equals to limit h tends to 0 fx plus h minus fx over h. So this fx is just a function, dummy function, so we can let fx as x squared. So yeah. Then how do we find fx plus h? So recall functions. X plus h is now the input. So fx plus h will become x plus h squared. And fx is just x squared. So we have this. And let's expand it out. So if we expand it out, it becomes x squared plus 2hx plus h squared, and we subtract x squared and divide it by h. So we see that x squared cancels, and this h also cancels with these h. So we have this. And what's h? H is a very, very small number. That means we can treat it as 0, because we can say that it's negligible. And that means that this 2x is the equation of the gradient of this function. So what does that mean? So let's sketch 2x, which will look like this. A linear function passing through the origin. So remember, the gradient of x squared must follow this. And let's see. When x is on the negative side, the gradient, all values of the gradient is negative, like this. And it becomes 0 when x is at 0. And it becomes positive again when x increases positively, right? So all these values here, these y values, represent the gradient of this curve at these certain points. So if we have x1, x2, x3, and x4, x5, then this value corresponds to the gradient at x1, and this y value corresponds to the gradient at x2, and this y value will correspond to the gradient at x3. Get it? And the same for the right part as well. Let's try one more example. So this time it was too simple. So I'm going to use a cubic function. Well, the function itself looks simple, but when it comes to the calculation, computation, it may not be that simple. So let's do the same thing. So let's sketch 4x cubed first. So the 4x cubed will look, it's a cubic function, so it will look like that. And let's estimate how the gradient of the function of the gradient will look like. So when x is negative, the gradient is all positive. And it's getting smaller, 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 and it becomes 0. And then it goes up again, right? Then we can see that the gradient will, the value of the values of gradient will start with plus, and it will reach 0, and it will go plus again. Now let's see whether it really works. So again, dy over dx equals to limit h tends to 0, this. And doing the same thing. So as I said, fx is just any function, right? It's a dummy function. So we can, for this case, we can let 4x cubed as fx. Then this fx plus h. So fx, we make it as 4x cubed. Then x plus h, we make it as 4 times x plus h cubed, because this is basically saying that the input is x plus h instead of x. And we subtract the normal function for x cubed, and we divide it by h. Sorry for the noise, there's a bit of congestion outside. But anyway, so we have x plus h cubed, so we can expand it out like this, or you can use binomial expansion to do it, or you can memorize it as well. So 4x cubed plus 12x squared h plus 12xh squared plus 4h cubed. And then we subtract 4x cubed and divide this by h. So again, we cancel 4x cubed, and we can also cancel h by dividing h here. So it yields 12x squared plus 12xh plus 4h squared. Again, what's h? H is a number that is very, very small. So it's almost 0. So we can treat it as 0. Not exactly 0, but we can treat it as a 0. So 12x times 0 will be 0. And 4h squared, 0 squared, 0. So this will be the equation of the gradient. And let's see. 12x squared will look like this. And we see that when x is negative, all values are positive. And when x equals to 0, the gradient equals to 0 again. And it will become positive again. So the same. x1, this y value will correspond to the gradient of this curve at this point, and x2, this y value will correspond to the gradient at this point, and same thing for the positive side. So we have seen two different cases using the first principle of differentiation. But as you can see, using the use of first principle of differentiation is very important because it's the fundamental definition, but it's very tedious. So we want to make a generalized formula so that we can directly compute the differentiated function. So we're going to learn several basic differentiation formulas for differentiation. So the first thing is when we have x to n, so any power with to x, if we differentiate it by x, so remember this means we're differentiating y in respect to x. So we have this. So remember when we had x squared, using this formula, this power will be the coefficient, right? And the original power of the function, this 2, will be subtracted by 1, so it becomes 1. Okay, so it makes perfect sense. The derivation is not important, but I'll just do so that you guys can understand why we have this formula. So any formulas for differentiation, we use the first principle because as mentioned before, it's the fundamental definition of differentiation. So dy over dx, always remember this definition, first principle. So we have this, and again this fx is a dummy function. So in this case, let's use fx as x to n. Then doing what we have done before, this fx plus h, so the input is x plus h, and this is the function. Then we have x plus h to n, right? And we subtract x to n divided by h. For this part, we need binomial expansion. So bi means 2, binomial to n, expansion, so expand it out. So we have x to n, nc1, xn minus 1 h, all the way, ncn minus 1, x1 hm minus 1 plus h to n. So that will be like this. So putting that back, we have x to n, nc1, xn. Alright, yeah, I'll just write it. Minus x to n over h. So again, we can see that we can cancel out x to n, right? And we can cancel out this h too, because every term here will involve h, at least one h. So that this h will be cancelled out, so it will yield this, and this h will also be cancelled out. So out of n minus 1h, we take out 1h, so there will become n minus 2 using the exponential property. And that will become h to n minus 1. So doing the same thing, h, we can treat it as 0. So all the terms here will involve 0 because the later term will be h squared. So h squared divided by h, it will involve h as well. So all the terms will vanish. So we have nc1 x to n minus 1. And what's nc1? So from combination, we've learned in counting principles, it's this. N factorial means n times n minus 1 times n minus 2 times all the way to 2 to 1, and divided by n minus 1, n minus 2 all the way. So they all cancel. So it yields n only. So it becomes n times x to n minus 1, which is the formula. So that's the most commonly used formula, differentiation formula. Second thing is something like when a function is multiplied by a constant. Then in this case, if we differentiate this, we just leave the constant and differentiate the function. So what I mean by leave is that we don't take it away, just put it back. So remember, for this example, we have 4x cubed. So this case, 4 is the coefficient and fx, this x cubed is the function. So if we had x cubed, let's say, then using this formula, we'll have 3 times x squared, right? So the power 3 will become the coefficient, and 3 minus 1, it will become 3x squared. But we had 4, so we multiply, we just keep 4. So it will be 12x squared, which is the answer. And 3 will be, let's say we have a constant. Then what happens if we differentiate a constant? So y equals c is a constant function, so you don't even need to do this. Because dy over dx, what is it? It's looking for the gradient, right? Y equals c is a constant function. It's a flat horizontal line. And then any x value, the gradient is 0 because there's no change in y. So the gradient must be 0. Or if you want the other way, so if you don't understand, if you don't want to use the graph, then we can use this again, because constant, that means c times x to 0. So x to 0 is 1. So I basically multiply by 1, which doesn't affect the equation. And using this formula, so this power is 0 here, using this formula and that, we just leave the constants, right? And x to 0. So using this formula, 0 becomes the coefficient, and the power becomes 0 minus 1. Which is 0 because we multiply by a constant. And it's, of course, it's assuming that x cannot be 0, because for this one, 0 to 0 is undefined. So it's indirectly saying that x is not 0. So we have this. Last, what if we have set of different terms? So for example, a function added or subtracted by the other simple function. Then if we differentiate y in respect to x, you just need to differentiate it separately. So differentiate this and differentiate that, and then just add or subtract. And that's it. These are the 4 very simple formulas that you must know and you must use well. So that's it for the simple differentiation. And before we directly move on to some other functions, let's quickly see how we can use this. So for example, just one example. So let's say we have x to 5 plus 2x cubed plus 1, let's say. So if we want to differentiate it, alright, so it's a combination of multiple terms, right? So we apply 4, right? So basically we have to differentiate one by one. So for this one, we can directly use this, right? We make this power as a coefficient. Oops. And then we subtract 1 from the power, so it becomes 5x to the 4. And this one, we apply 2 and 1. So constant, we just leave it, and this one, the power becomes the coefficient, and subtract 1 from the power, so x squared. And lastly, the constant. If we differentiate constant, it becomes 0. So that's it. So we have this if we differentiate that function. And that's it for simple differentiation with polynomials only. Oh, and for the proof of this, you can use the first principle as well. I skipped it because you don't really need it, but if you want it, you can ask me. I'll answer it if any one of you ask me. It's very simple. You can try it by yourself using the first principle. Now, we have seen polynomials, right? So x to something, x to n, right? But what if we have on like the other functions? We've learned a lot of functions like trigonometric, log, and exponential. Or also rational and irrational, but rational and irrational we can group it as polynomial because one thing that I haven't really talked about. So for example, rational, if we have this or like that, then we can simply make it into an exponential form, x to minus 1 or x to minus 3. Then we can apply this, right? So power, put it out, and then subtract 1. Power, put it out, subtract 1. Same thing for irrational. So if we have root x or cubic roots x, then x to half, x to a third. Then this half becomes the coefficient, half minus 1, and this third becomes the 1/3 becomes the coefficient, and subtract by 1. Simple, right? So if we differentiate it, we'll have 1/3 times x to this, that, and this. So very simple. Now we are going to look for some different functions, and let's start. So let's start with sine x. If we differentiate sine x, we have cosine x. I strongly recommend you to memorize this. It's not hard to memorize, but for this one I'll give you the proof as well. So I'll tell you why it becomes like that. So again, for any proof in differentiation, we use the first principle. Oh, by the way, if you're in SL or IGCSE, you can skip this proof because you don't need it. Maybe for HO you may need it. So again, fx is a dummy function. We can for this case we can let fx as sine x, right? So x plus h. Now the input is x plus h. Then if we put x plus h into this function, we'll have sine x plus h. And fx is just sine x. And we have this. Now, we have sine x plus h. So for all those first principle, so all those questions involving first principle, we are aiming to cancel this h away. So this h in the numerator, it's inside sine, right? So we have to think of a way to move it out. So what we can do, we can use compound angle formula. Right, so this is where the important things come. So cosine h, and what's h? H is a very small number, almost 0. Then if you remember the graph of cosine, this is a graph of cosine. So when x equals to 0, cosine is 1. Then when cosine approaches to 0, it will become 1. So we can treat it as 1. And if it's 1, then it's just sine x, and you can cancel out. This is a problem, so a sine curve looks like this, and when sine approaches to 0, when x approaches to 0, sine approaches to 0 as well. So this sine h, we can consider it as 0, and h is also considered as 0. Then, but they're not exactly 0. That means these two are constants. Then why don't we cancel them out? So it yields cosine x. And some may ask, so this is sine h and this is h. So although they're very small, but they don't have to be the same, right? For this case, so for more precise definition, you can't use first principle. What you have to use is the other definition of differentiation called the epsilon and delta definition, and you can learn it if you major in economics or mathematics, and you will learn this in mathematical analysis university year 2 level math. So I'm not going to talk about it for this case, but yeah, so using this idea, we can see that if we differentiate sine, we have cosine. So that's the proof. Second, then what if we differentiate cosine? We have negative sine x, and the proof is exactly the same except for the fact that you just need to expand cosine x plus h using the compound angle formula for cosine, not sine. That's it, and it's exactly the same. Right, so for IB students, you have to know tangent as well. So if you differentiate tangent, it becomes secant squared, which is 1 over cosine squared, cosine x squared. But even if you're in SL or IGCSE, you may still be asked to differentiate this, not by this, but so we know that tan x can be written as sine x over cosine x. So it's a quotient form, right? And later you will learn a formula for differentiation when the two functions are multiplied or divided each other. So since you need to know the differentiation of sine x and cosine x, you must know this as well. But yeah, that's the later case. So these are the 3 trigonometric functions, and we have 2 more, not trigonometry but exponential. So y equals e to x, and this e here is a special irrational number like pi, called the natural constant, and it's 2.71 and so on. And as I said, it's irrational, so it just keep going. Yeah. Anyway, so if we differentiate e to x, we have e to x again. The proof is not important at all. You can use this again. Yeah. And 5, we have, what if we have ln x, which is a natural log x. So the base of log becomes e. Then if we differentiate it, we have 1 over x. Okay? So these are the 5 special functions that we have to know. Now here comes the very important part. further differentiation rules. So first we start with chain rule, and bear in mind that this is the most important rule in differentiation, because basically this allows you to differentiate any function which are differentiable. So what's chain rule? Before we directly move on to chain rule, I'll ask you something. So for example, when you had like exponential equation, so something like this, or logarithmic equation, something like something like this. How did you solve it? You use substitution, right? Let e to x be something like k, then e to 2x becomes k squared, e to x is simply k, and we form a quadratic equation. Very simple, right? It's very simple. And the same for this. So if we let this as a, then that becomes a plus, and using the log property, we have this. And if we multiply a every term, again, we have a quadratic equation. So when we have something that is not familiar, what we can do is that we use substitution to make it familiar to us. Same thing for chain rule. So how we use chain rule is that when we have an unfamiliar function to differentiate, we make them into a familiar form. So for example, let's say we have to differentiate sine 7x. What do we know about differentiation of sine? We only know sine x. When sine x is differentiated, it becomes cosine x. But now it's transformed, right? It's a horizontal stretch by a scale factor of 1/7. Then how do we differentiate that? So we let 7x be something like u, like one single variable without a coefficient. Then 7x equals to u, so nothing changed, but except 7x just becomes u, so sine u, right? Now here comes why this notation is important. So we want to find dy over dx. So y differentiated by x. Then if we want to find dy over dx, we have to differentiate this in terms of x. So since y equals to this, we write it as d sine u over dx. So y sine u dx, okay? But here comes the problem. We could directly have cosine x because the function is in x, and we differentiate by x, so the variables are synchronized, and it's just a simple differentiation. But now the variables are not synchronized. The function is in u, but we have to differentiate in x. Then we can't directly differentiate it, right? Then should we change u in terms of x? No, because it's just going backward, right? Then what we can try is that we can change dx, but we can't just cross it out and then write du, because that's affecting the equation. The equality no longer holds if we do that. So what we can do is that we can either add 0 or multiply by 1, which do not affect the equation. So in this case, I'm going to multiply 1, but which one? du over du. So again, you have to understand the definition of du and dx. Dx, as I said, it's the instantaneous change in x. Du is instantaneous change in u. So simply that's the definition of du, and then for not du, dx, and that's the definition of du. So du is just one variable. Dx is also a variable. Dy is also a variable. Okay. And since this is multiplication, we can switch the order. Switching the order in multiplication does not affect the result. Now, we have to differentiate sine u in terms of u, and that's simply cosine u. But what about du over dx? What does this mean? We are looking for the instantaneous change in u in respect to the instantaneous change in x. Simply, we have to differentiate u by x. But what's u? U is 7x. U is 7x. Then if we differentiate at u by x, we have 7. Why? Because x to 1. So using the basic formula, this one, we have that, right? 1 goes to the coefficient. 1 minus 1 is 0. X to 0 is 1. So we have constant. Then du over dx is 7. So we have 7. Now, replace u by x back. We have, so this is the application of chain rule. And with chain rule, you can simply differentiate anything. Anything that is differentiable, okay? Another example is, let's try one polynomial, but hard polynomials. So something like x cubed plus 2x to the power of 17. So I'm pretty sure no one would dare to expand this out and apply this. Don't do that, okay? To the power of 17, it's insane to expand it out. So what we can do is that we know how to differentiate this. But when the base is not just x, but a function of x, then again we use substitution. So let x cubed plus 2x be u. Then y equals to u to 17. So doing the same job, we want to find dy over dx. So y differentiated by x. Then if we differentiate this, we will first have the u to 17 over dx. Because y is u to 17, so I just wrote y as u to 17. That's it. And again, the variables are not synchronized, so we can't directly differentiate it. So what we can do is that we multiply by 1 du over du, and then switch the order. Now we can differentiate it because u to 17 differentiated by u, so the variables are synchronized, so we can use this, right? It's just u to n u. So 17 times u to 16. Now du over dx, again, it means we differentiate u in terms of x. Then we need to know what u is, and in fact u is x cubed plus 2x. That means if we differentiate u by x, we have 3x squared plus 2. So multiply it back, we have this. So, and replace u by x again, then we have 17 times 3x squared plus 2 times x cubed plus 2x to 16. Okay, good. Last one. I'm not gonna do it entirely, but I'll ask you to do it by yourself. So, for example, we've done a horizontal stretch of trigonometry, But what if we have something like cosine to 7x, which means that cosine x entire thing to 7. It's clear. So one thing, cosine 7x is not the same as cosine x to 7. This one means this, the entire thing to the 7. This one, the angle, the input of x to the 7. So they're entirely different things. But yeah, so if you have to differentiate this, then what do? So a lot of students, when they see cosine, they recall this, and it's absolutely right because you have cosine. So if you have the differential cosine, you'll have negative sine x, right? But in terms of substitution, what do you have to substitute? That's the problem. Because some students try to substitute the entire thing. That's not the case. If you see this, you should be able to recall this. This. Something to the power. Something to the power, right? So you just need to let u as cosine x, because you can substitute anything, right? And then perform the computation like this. Okay, so that's it for the chain rule. Now, two more rules to know, then you're done with basic differentiation. So first one was chain rule, second one is the product rule. So as mentioned before, when I talked about tangent, so we've seen a case where multiple functions are added or subtracted, right? But we may also have a case where multiple functions are multiplied or divided. So product rule is used when two functions are multiplied like this. So fx times gx. And if we differentiate it, we have f prime x times gx plus fx times g prime x. So first thing, we differentiate the first one, we leave the second one. We leave the first one and we differentiate the second one. Okay? The proof for this, you can also use first principle of differentiation, but it's quite difficult, so I'll just do it for you. But again, you don't really have to know the proofs unless you're HL. But for this, even for HL, you may not need it. So for those who are just interested, you can see it. So dy over dx is always this. But now fx, so for this one, so we have fx here. Okay, I don't want to confuse you guys with the variable, so I'll use y as something like gx times hx, so two different functions. So it's a dummy function, so it can be anything, but just in case. So let's say we have two different functions like that, and where this is fx. Okay, then x plus h, so input becomes x plus h. Then every x here is replaced by x plus h. Then the input here, it becomes gx plus h times hx plus h. And we subtract the original function, which is simply that. So we have this. And we divide it by h. Now, this is the tricky part because, as you can see, there is no way to take h out, like in sine, the compound angle we did, because the functions are not defined. So if they were trigonometric functions, then we can try doing that, but we don't know. We can't guarantee that they're trigonometric functions. So what we can do is that, remember, not affecting the equation, but we can we can either add 0 or multiply by 1. And I'm going to, for this time, I'm going to add 0, but this time the 0 will be, let's see. Yeah, I'm going to add this. So same term, added and subtracted. Then if we add them, it's 0, right? So I added 0. Basically, I did nothing, right? So the equality still holds. Now we're going to group it. So the common factor here is hx plus h. So we take the common factor out, and we have gx plus h minus gx. And for this one as well, the common factor is gx for this. So take it out by gx, and then we have this. And we can separate these two terms into two different fractions. This and this. And again, what this means is that for anything on the right, all h tends to 0. So h tends not this h. This is just a function, okay? So this h, they tend to 0. Again, here we have h2, right? So this also, it kind of works like distributive law, okay? What's this? It's exactly the same as the first principle, right? So if we have x plus h minus fx over h, then we have the differentiated fx, right? F prime x. But this case, we have g with limit. Then this becomes g prime x. And so that one becomes g prime x. But what about this? hx plus h. And what's h? H is as negligible as 0, so we can treat it as 0. So we have this, right? So, well, it's the order of matter. So if we have this, then first one, oh, sorry, yeah. Oh, it was right. So if we have this, first thing differentiate it, and second thing leave it. Plus this one is, again, that is h prime x, and we have gx. So we have h prime x times gx. So writing it back to what we know. So first thing differentiated, second function just leave it, plus first function leave it, second function differentiated. So that's the proof for the product rule. Okay, good. And the last one is quotient rule. When a function is divided like this, then what we can do is that, what the formula is, that dy over dx equals to first thing differentiated, numerator differentiated, denominator leave it, minus, so the order matters for this one, numerator leave it, denominator differentiated, and divide by denominator squared. Unlike the product rule, this one, the proof is pretty simple because you can use chain rule and product rule. So this quotient form, it's a rational function, right? So we can write it as an exponential form. So it doesn't have to be in the denominator. So two functions multiplied, right? Then we can use product rule. And again, we have something inside the function, something with the power, right? Then we can apply chain rule to make it into this form and then follow the calculation. So the proof should be simple. So I'm not going to talk about it for this case. So that's it for the further differentiation rules. I'll try two questions with you, and then so one for product and one for quotient, and then that will be the end of this video. So an example for product rule. So let's say we have, I'll make it very simple. So okay, we haven't touched log, so let's do this. X times ln x. So okay, it's too simple. I'll make it as x cubed times ln x. It's simple too, but yeah, anyway. So if we have to differentiate this, simple. First thing, differentiate it. So x cubed, that means we can apply this, right? Then 3x squared. And we leave the later function. Plus, now we leave the first one and we differentiate ln x. But ln x, what is it? It's natural log x. So if we differentiate it, it becomes 1 over x. So it becomes this. Very, very simple, right? Quotient rule. So I'll do an example. Tan x, let's say. Why tan x? Because tangent x can be written as sine x over cosine x using the basic trigonometric identity, right? So numerator, denominator. Then so quotient rule is when you have this, differentiate the numerator, leave the denominator, minus, leave the numerator, differentiate the denominator, over the denominator squared. So do the same thing. Numerator is sine x. If we differentiate sine x, we have cosine x. And leave the denominator, which is cosine x. Minus, so fx, leave the numerator and differentiate denominator, but if you differentiate cosine, you have negative sign, over denominator squared, so cosine squared. Then the numerator becomes cosine squared plus sine squared. And what's cosine squared plus sine squared? By identity, it's 1. So we have this, which is secant squared. That's why we have this. Okay? Good. So that's it for today. So we have covered the basic differentiation and some further differentiation rules. And for next lesson, I'll talk about some application of differentiation. So finding local maximum, local minimum, and something more about gradients. Alright, that's it for today. Bye.